Okay, here's what I want you to do. With the person sitting next to you, take a look at the warm-up, answer the questions, and let's see what you guys come up with. Okay, for the first one, quantitative.
Yes.
Second one, qualitative. Next one, quant, qual, quant, qual. Yes?
Yes.
Okay. So quantitative is going to involve a number with a unit. That's basically how you differentiate the two. All right, let's talk about scientific method. So basically, when you are making observations and collecting data, we are going to be using the tried and true method known as scientific method. Robert Boyle is the one that pioneered the use of scientific method. He put all of his work into tables. He outlined the procedure and the apparatus used. And his records allowed people to repeat his experiments. Now, let's take a look at the next page. On the next page, they outline the different steps of scientific method. So these are things like observations, and then observations could be quantitative or qualitative, depending upon whether there's a number and a unit or not. Observations can also be categorized as physical, meaning related to color or the temperature of something, or maybe its density. Or they could be chemical observations, which are related to how does it chemically react or behave during chemical changes. Okay? Then we have a hypothesis, which is generally an if-then statement. And then experimentation is going to involve coming up with a way to test things. And then frequently, when we do experimentation, we will have things called sources of error. Now, be really careful with sources of error. Sources of error are different from mistakes, okay? So things that we have no control over are going to be sources of error. Mistakes are going to be things that humans make. Okay, and that's generally how you differentiate between the two. Then we have a statement of a theory. So if you've gathered enough information from experiments that are done by many different people, then you come up with a theory, and then theories can lead to models which explain observations, and then sometimes we get a law out of it. So how do we differentiate between theories and laws? So laws are going to be related to math. Laws are going to be 100% measurable. Okay, so let me give you an example. The law of conservation of mass, which is sometimes called the law of conservation of matter. This basically says that when I have a chemical reaction happening, let's say I have magnesium reacting with chlorine to produce magnesium chloride. Whatever mass of reactants I have, let's say I have a gram of magnesium and a gram of chlorine, okay? When you add those two together, I would get 2 grams, agreed? So when they say mass is conserved during chemical reactions, when chemical reactions occur in a sealed container, you shouldn't be losing anything. So that means that theoretically, the mass of my reactants should equal the mass of my products. This is measurable. This would be an application of the law of conservation of mass, okay? So the sum of the reactants equals the sum of the products. Okay. Here's what I'd like you to do. I want you to do number 3 in the quick check. Okay. And let's see what you guys come up with. Okay. So for the first one, the balance used to weigh the product was not zeroed. Totally a mistake. Okay. The next one, the product being weighed was damp. Source of error. The balance used to weigh the product only reads to the nearest centigram. Perfect. Your partner read the value for the mass incorrectly. And then you made a subtraction error when determining the mass. Good job. Next page. Okay, let's do a little bit of review of scientific notation and some basic graphic stuff. So on the next page, they talk about using scientific notation. Generally speaking, in this class, we will be reporting things using standard scientific notation. Okay, they often omit the word standard when they're talking about scientific notation, but I'm not going to here because I need you to understand that if you have a really small number or a really large number, when you report it using scientific notation, it has to be standard. That means you will have one non-zero digit to the left of the decimal. So if you're using something like this, this is one non-zero digit to the left of the decimal. Okay, that would be standard scientific notation. Remember, you have a mantissa, which is the decimal portion, which is this part right here. Okay, and then you have the ordinate or the exponential portion, which is right here. Okay, positive exponents in the power of 10 tell you that I have a really large number. Negative exponents on the power of 10 indicate that it's a very small number. Okay, so if you have a positive exponent, you move the decimal to the right. If you have a negative exponent, you move the decimal to the left. Do I need to go over this, or can you do the quick check without me? Okay, you try the quick check without me. Let's see what you come up with. Okay, did you guys get something similar? Okay, any questions for me or anything? Perfect. Okay, let's talk about multiplying, dividing, adding, subtracting with scientific notation. You're going to be using calculators, and if you go on to take AP, they now allow you to use calculators. So I'm actually not going to be too worried about discussing how to multiply and divide in scientific notation without a calculator, okay? So here, that's kind of what they're doing. They're saying if you're multiplying two numbers in standard scientific notation, you would multiply the mantissas together, and then you would add the exponents together. If you're dividing, you would divide the mantissas, and you would subtract the exponents. Okay, let's go to the next page. And there's actually a special keystroke on your calculator that I'm going to teach you how to use. So let's go to the next page and let's take a look at these practice problems so that I can teach you guys how to use those special keystrokes. Okay, so on the next page in the practice problems, let's take a look at number one. Obviously, number one is pretty straightforward. You could do that without a calculator if you wanted to, but let me explain to you how to use the second E button on here. Okay, so for number one, what you're going to do is, I'm going to write the keystrokes down for you. It's going to be 4, and then the second key, which is in the upper left-hand corner, and then you're going to press the E. So above the 7 is a comma button, and then can you see above the comma it says EE? Okay, so press the comma button once, and an E will appear. And then you're going to type in a 3, which is this exponent on the power of 10. So what this stands for is 4 times 10 to the third. Okay? And then we're going to do times 2 second E 4 and then enter. So this would be the second number that you've got in scientific notation. Does this make sense? Now the reason why I teach this to you is because if you tend to use the, bless you, if you tend to use like the caret function, or if you have an older graphing calculator, I know that the newer ones allow you to have like 10 with an exponent on the screen. It wasn't always that way. If you don't use this, you run the risk of having an answer that is 1 decimal place off, which can be really annoying, okay, because then you just get it wrong, right? So when you put this in your calculator, 4 second E3 times 2 second E4, enter, you probably got a really big number, okay? And I'm assuming you know how to convert this into scientific notation using the calculator. If you don't, if you press mode and then use the arrow key to go over to psi and press enter on psi and then second click to get out of there. Hit enter on the screen that had your answer and it will convert that answer into scientific notation for you. Okay, so you should now have 8E7. It would be deemed incorrect for you to write 8E7. This would always be wrong. You would have to write it as 8 times 10 to the 7th. Does that make sense? Okay. Okay, so let's take a look at number 2. Let's do this in a different color. So for number 2, this is going to be 9.9 second E5 divided by 3.3 second E3, enter. I got 3E2. Did you get that?
Yeah.
Okay. So that would be equivalent to what? 3 times 10 to the second or 300. Does that make sense? So I just want to make sure that you understand how I'm doing the second E on the calculator because this is only the beginning of math that we do in this class. So I don't want you to be confused for a second on the second E stuff. So anybody have any questions on that or are we okay? Okay, so silence means we're fine. Okay, now, do you want to try like number 3 and number 5 on your own? Okay, so try 3 and 5, and let's see what you guys come up with. And then 7.5 times 10 to the second. Okay, so we're okay. I can go on. Awesome. Okay, let's take a look at adding and subtracting. This kind of stuff used to be a big deal before the AP exam shifted a little bit. You had to do a lot of math in your head. So I'm not so concerned about this adding and subtracting in scientific notation either. So we're just gonna shift over to here. Let's come over here. Let's review some of the rules for exponents, okay? So here, if we've got number 1, I am assuming you recall that you're going to be multiplying the 3 and the 5 in the exponents together, so this would be 10 to the 15th. Yes? Okay. For number 2, you would have to distribute this 3 to each one of these. This would be 2 cubed times 10 to the 6th. 2 cubed is 2 times 2 times 2, which is what, 8? Okay, so this would be 8 times 10 to the 6th. Number 3, you would distribute the 2. This would be 5 squared times 10 to the 8th. 5 squared is 25. It would be foolish for you to leave an answer like that if I wanted the result in standard scientific notation, because this is not standard scientific notation. You would have to move this decimal over 1. So this would become 2.5 times 10, which will raise the exponent on the power of 10 by 1, since I moved it 1 decimal place to the left. Easy enough? Okay, let's talk about graphing. Okay, now for graphing, you know that there is an independent and a dependent variable. And typically when we are using time as a variable, time is almost always going to be independent, okay? So that means that time is probably going to be on your x-axis. We're going to be putting data into data tables. Make sure that if I ask you to create a data table, you are using the Xavier Lab Report template. I will give you a copy of that. You want to have a title. Let me stop this video so that I don't lose the